Okay, class, in this section, we're going to talk about section 3.3, 3.2 and 3.3. 3.2, which is the derivative as a function. And in 3.3, we are going to introduce the rules to compute. That is going to be the base for having techniques to compute or to make differentiation in a function. Okay, so let's go with the derivative as a function. Well, we introduced already the concept of derivative at some particular point for a given function. You have seen this picture before, this graph before, and just to remind you, the derivative of a function in a particular point x is going to be the slope of the tangent line at that point. The tangent line of the function at that particular point. So, and we know that the slope of that tangent line represents the instantaneous rate of change of the function at that particular point. We introduced that definition already. What we're going to do now is we are going to repeat that concept to every point within the domain of the function. Not only for this particular point, but also we are going to repeat exactly the same procedure for any other point. Okay? And when you do that, you are going to define another function, which is the derivative of a given original function. And what is going to be that function? That function will represent in each particular point the instantaneous rate of change, which is equal to the slope of the tangent line to the function at that point. You understand now what is the definition. So now for every point that we have within the domain of the original function, we are going to define the derivative. And that is going to create another function, which is the derivative function. Now, the important point here is that it might be the case that at some moment or at some point within the domain of the function, that limits that define the derivative probably doesn't exist. So that the consequence of that is that the domain of the derivative function is going to be a subset, or is going to be included into the set of the domain of the original function. Okay? But more important than that, and this is what I want you to keep in mind, is what the sign of the derivative is telling to you about the original function, because that is the most important thing that you really need to keep in mind. So look at here. For instance, here we have a quadratic function in which the curve is represented with this continuous black line. Okay? And we show the derivative at some particular points. Which are the blue dots that you see over here. You can see, for instance, that in this interval, let's say from 0 up to 3, okay, which is the vertex of this parabola here, okay, of this quadratic equation, you can see that the original function increases in that interval. If you look the slope of each one of the tangent line at those particular points, for instance, in here, in 0, for 1, for 2, okay, you can see that the tangent line, the slope, is positive. In other words, the derivative within this part of the curve, I mean from 0 to 3, the derivative always is positive. And you can see at the same time that the function is increasing. So what is the conclusion? That whenever the derivative is positive, well, the function is increasing in values. And that's why the slope of the tangent lines are positive. Okay, so you can see here that this tangent line, the slope is positive, In here, the slope is a little bit gentle than this one, which is telling to you that instantaneously the function increase, but not as fast as it's increasing here. And exactly the same here respect to this one. Okay? So if we go to the other part of the quadratic function, let's say from 3 to 6, we see that the black curve is decreasing in value. As the values in the independent variable are increasing, the function is decreasing. And you can see here that the slope of the corresponding tangent line at these points, what are the slopes? Well, the slopes are negative. Okay? So you can see here this red line, that is the tangent line at this point. Okay? Well, that slope is negative. In here, the slope is negative. And in here, the slope is negative. What is the conclusion of that? That whenever the function is decreasing, the derivative is negative. Now look at this here. Imagine that we put a glass over there. Let me see if I can zoom a little bit on here. Let me zoom this. Make it bigger, 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 very big. Okay? So if I tell you, well, look around this point, a little bit around this point, okay, you can see that the function, the black curve, a little bit around that point is almost a constant function. What is the meaning of a constant function? That within a very small interval around this point, the function doesn't change. So the rate of change in that interval really is 0, because the function is always constant in a very small interval around there. So what we expect, that the tangent line at that point, the slope of that tangent line is going to be equals to 0. So when the function is constant, then the derivative is equals to 0. That is the conclusion of that, and that is very important to keep that in mind. Okay, so let me go again to 100. Well, probably 100 is too small. Okay, and well, this is the derivative function. It's basically to define the derivative or to compute the instantaneous rate of change of the original function at every point of the domain. Or in other words, to compute the derivative at every point, and then you create the function. And that's what I say over here. You know that that slope of that tangent line is this limit, and now we are going to compute that at every point of the domain of the function. That is the derivative function. Now, as I mentioned here, what is going to be the condition to exist the derivative? That this limit is going to exist. And it is not always the case. That's what I say over here. Now we extend to all point values of the domain of the target function, making the derivative another function. Okay? But not necessarily the derivative function is defined for all the elements from the domain of the original function. That's what I mentioned before. So as a conclusion of that, the domain of the derivative function is going to be smaller or equal than the domain of the original function. In other one, it's going to be a subset. Okay, so that keep in mind, because it's very important to understand that. But that is the definition of the derivative function. It's just to compute the derivative, you know everything about the derivative at one point, then we're going to extend that concept to all the points within the domain of that original function. Okay, now let me go in here with this example. This is an example that I create for you guys using a very simple polynomial function in which the degree is 3. Later on, you're going to learn that this one here, this polynomial here, in which the degree is 1 power lower than the original function, is really the derivative. So what you see here, this quadratic function, is the derivative of this original function. And I plot that in Desmos, just to illustrate and to reinforce the concepts of the derivative, because this is the most important thing that I want you guys to be focused with. Okay, so this cubic function, this is the function, the original function here. Okay, and in Dutch blue, I graph the derivative of this one. Okay, as you can see here, there are intervals in which the original function is increasing. There are some other intervals in which the original function decreases, and there are some other portions in which the original function increases again. Okay, what is going to be the behavior of the derivative? Let's start here with this branch. Okay, so this part until this point. So you can see that the original function is increasing as the independent variable goes to 0 in the negative direction. Okay, so it's increasing the value, the function is increasing as well. Well, look how the derivative graph. The derivative graph in the positive side. Okay, but anytime in magnitude, even though if the derivative is negative, anytime the derivative is smaller, 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 and smaller, have a smaller value. Why? Because if you make a target line at this point, the slope here is higher, but if you make the tangent line at this other point, even the slope, still the slope is negative, but the tangent line, the dipping is going to be a little bit gentle. That's why the derivative is decreasing in value, in magnitude. But the most important thing that I want you to remind at this moment is that if the function is increasing, the derivative is going to be positive. Okay? In here, the function is still increasing. It's still increasing, so the derivative is still positive, but you see that there is a point in which the derivative is equal to 0. What happened with the original function? Well, at that particular point, if you look around that point, the function is almost constant. You see? So you see here that the tangent line is horizontal. What is the meaning of that? That the slope is 0. And what is the meaning of that in terms of rate of change? Well, that the original function in that particular interval, very small interval around this point, the original function doesn't change. Always the values are the same, so doesn't have any rate of change. And because the rate of change is 0, then the derivative at that particular point is 0. So the slope of the tangent line at that point is 0, is a horizontal line. So horizontal lines derivative is 0. Horizontal lines slope is 0. Okay, so you can see here that between this point in here, that is a negative number, all the way down to 0, the function now is decreasing in values. Okay, so you can see that from this point to this one, now the derivative is negative, because if you draw in here any tangent line, the slope is going to be negative. The tangent line is going to deepen down. Okay, that's why the values of the derivative function is negative. You see the correspondence now? So, increasing derivative is, if the function increase, so this is a notation that you can use when you're going to make your exercise. If the function increase, the derivative is positive. Okay? If the function decrease, the derivative is negative. Okay? Is the function start to increase in here, like we can see in here, the derivative, so the function is increasing, well, the derivative is positive. And anytime in here, the derivative function have higher values. Of course, because if you take the slope here, and you take the slope here, and you take the slope here of all these tangent length, of all these tangent lines, you're gonna see that the slope of this one is higher than this one, the slope of this one is higher than this one, and the slope of this one is higher than this one. Okay, because this tangent line dip outwards more than this one. So the rate of change is higher. Okay, that is the other point. But what happened in here? That's what I put in this graph. What happened in here? If you make this very big again, let me make here a zoom. If you consider just a neighbor point around this point, you can see that the function doesn't increase, neither decrease. The function is constant. Okay, the function is constant. Always. Doesn't change. Because doesn't change, then the derivative is going to be equals to 0. Exactly the same here. The function is constant, then the derivative in here is going to be 0. And this is the derivative of the function, f prime and f prime. Here the derivative is 0. Okay? Well, perfect. That's what I want you to keep in mind on this, because that is very important. Okay? And you're going to find those kind of analysis in your exercise or in your homeworks. I don't know if I asked in your notes to derive this, the derivative of this function. But if I haven't, just when we never finish this section up to 3.3, go back and check and compute the derivative of this one and make sure that you're gonna get this answer. Okay? What other comment I want to make here? Well, some considerations. For instance, in here, the function is decreasing, so the derivative is gonna be negative. So let me make in here, the derivative is going to be negative. What happened here? The function is increasing, so the derivative is going to be positive. But what happened here? Look at here, the derivative is negative for all these points around to 0, and in here, the derivative is positive for all those points around to 0. What happened in 0? Well, the derivative doesn't exist, because from this part, the limit is negative, and from this part, the limit is positive in the definition of the derivative. So the derivative doesn't exist, because you can see here that the tangent at this point of the function is a vertical function. And what is the slope of the vertical function? In here, that slope is undefined because it's infinite. Okay? So, in this point. So, whenever you have a very sharp point here in the function, or a discontinuity, then the derivative is not going to exist. That's what I told you. That the derivative, first of all, is not defined in all the points of the domain of the function. Look at that, the function is defined here. The function in here is equal to 0, but the derivative is not defined there because that limit doesn't exist. Okay? The other conclusion of that is that if the function is continuous, not necessarily the function have a derivative in all the points. Okay? So, if the function have a derivative in a point A, the function is continuous in A, but the reverse is not necessarily true. If the function is continuous, then the function have a derivative in that point, not necessarily is true. That is the reverse statement of this one. And this is why I include this exercise. This function is continuous here in 0, but in 0 the derivative doesn't exist because the slope of the tangent line is infinite. Okay, exactly the same in this example. Okay, in this example, what happened? That the tangent line at this point of the function, the slope of the tangent line, the slope is infinity. So the derivative at this point does not exist. Okay? So that is something that I want you guys to keep in mind. Okay? This is another situation that have to do with this theorem that you have here. If the function is not continuous in A, well, the function doesn't have a derivative at that point. And this is what you see here. In here, how is the slope of the function? In this side is positive. How is the slope of the function in this side? Well, it's positive as well, but the derivative in this point doesn't exist. The derivative doesn't exist because it's discontinuous. Okay? So what I have in here is just a summary when a function is no differentiable. Okay? I mean, when the derivative doesn't exist. Doesn't exist when you have a corner or sharp point. That's what I told you in here. Sharp point. It's not continuous. It's not continuous like this one. Or at that point, the tangent is a vertical. Like this example here. The tangent is a vertical. So that slope doesn't exist because it's infinite. So the limit that defines the derivative function doesn't exist. It's infinity. Okay? Perfect. This is just an example you're going to find in your homework exercise like this, in which you are giving with the graph of some particular function, and then you need to define in which part of the domain of the function is continuous, and in which part of the domain of the function have a derivative function. So for instance, we can see that this particular function, the derivative exists between 0 and opening 2, because in here you have a corner or a sharp point. Okay, so the derivative doesn't exist here. Okay, and also is continuous opening 2 all the way down to 4. Okay, in this particular point, what is going to be the value of the derivative? Well, there is no change of the function, so the slope is 0, the derivative is 0. That's what I put it here. Okay, so in this part of the branch, how is the derivative? The derivative is positive. Why? Because the function is increasing. And in this part, in this branch of the function, the derivative is negative because the function is decreasing. That's what you have here. Is positive, and in here is negative. In this part, the derivative is going to be very large, and large. In other words, doesn't exist. Because this is a sharp point. So the derivative here is infinite. Okay, goes to the infinite values. What else I can tell you? That even though Even though in here the derivative is positive, in magnitude the derivative have any time lower values. Of course, because the slopes at any point are going to be the tangent line at any point when you move in this direction. In this direction here, the slopes are gentle and slower, lower and lower, because those tangent lines are gentle, more gentle and more gentle. What is the meaning of more gentle? The dipping is lower, lower and lower until they reach the zero. Okay? Exactly the same behavior that is described here in this sketch. What is this? What is this line? X equal in which the derivative is not defined. Well, it's going to be a vertical asymptote for the derivative function. What is this line? X equal what? 2. Okay? Perfect. Well, let me go to the final section of this first half, that is section 3.3. Today is Tuesday. Okay, you're going to have one more day to review this part. We're supposed to cover 3.1 to 3.3 up to Wednesday. That is going to be tomorrow. But let me introduce here section 3.3, which is the rule of differentiation. This section is very, very short. It's very, very short section. What we are going to describe here is, well, what is the derivative when we have the addition of two functions? Okay, so actually I don't like, I screenshot this from some place, but I don't like this notation. So I prefer to write this in this way. F and G, this. Well, assume that this function accepts derivative everywhere, and this function accepts derivative in this way. If this function accepts the derivative and this function accepts the derivative in all the corresponding domain, if you add the function, then the derivative of the addition is going to be the addition of each one of the derivative function. That's what this is telling to you. So it's like to apply the distribution property of the differentiation. So you distribute the differentiation operation into the parentheses. So that's what this rule is telling to you. What is the derivative of a constant function? You know already. A constant function is a function that doesn't change for all the values of the independent variable. So the rate of change is 0. So any tangent line is going to be a horizontal function, so the slope is going to be 0. That's why you have this. If you have a function that they accept the derivative everywhere, okay, and you multiply that function by a constant, then the derivative of this function, this resulting function, is the constant multiply the derivative of the original function. That's what this is telling to you. This is very important, and you're going to use this a lot. So, for instance, if you have here this polynomial, s to the third power, and you compute the derivative of that one, how do you compute the derivative? You're going to bring the exponent down, 3, keep the independent variable, and then you subtract 1 to the original power. Is 3 minus 1, so this is going to be 3s squared. This is the derivative of this one. Look at here. The derivative of one polynomial function is a degree, 1 degree lower than the original function. You see? So now you're going to be able to compute the derivative of this one. So we lower the exponent and put in front of the variable, of the independent variable. So it's going to be 3 times 3, which is 9, x. Then I subtract 1 to 3 squared. And in here, the next one, I draw this one here, 2 times 2, 4, s, the derivative of s is going to be 1, and the derivative of a constant function is 0. So this is the derivative function. Okay, now you are able to solve this. Now you know where this is coming from, this one. Well, this is all about section 3.1, 3.2, and 3.3. Okay? Now, you're going to see in your textbook that we compute the derivative of the exponential function. I include this just to show what is the slope, okay, or what is the derivative of the exponential function at 0. And this one here is the equation of the tangent line at this point 0 and 1. Okay? And in here you have the result. The derivative of the exponential function is itself. In your textbook, if you are interested in that, you have a derivation of this, but the most important thing that I want you to remember is that the derivative of the exponential function is itself. Okay, well, before finish this video, in here you will see the lecture notes for these sections 1 all the way down to 3 for chapter 3. Okay, remember what is the dynamic that we follow in our course. So once that you finish to review your lecture, go and make this exercise. So this exercise is from your lecture. Okay. In this one is an interpretation of the derivative function. This example is very important. Remember the one that I discussed in the lecture, and that was in the previous one. Okay, in here, well, you need to apply the definition of the derivative to find the derivative of this function. Okay, and then evaluate the derivative at this particular point. You will find exercise like this in your homework. So you have here functions and you have here graph of the derivatives. You need to make the match. Okay, that's what we discuss in the lecture over here. This kind of things, okay, and also this type of thing that we were discussing. So you need to follow that kind of reasoning in order to make this type of exercise. Okay, this type of exercise are very good to check if you understand the concept of the derivative. So you're gonna have this in your homework, and I believe so in your quiz, and for sure in the test I'm going to include something like that. And in here, what I want you is to analyze the slopes for each one of these functions. Okay, very similar to the one that I discussed in here. Okay, so perfect. This is what I have to say in this. So remember that right after this, on Thursday, we're gonna finish this first half of the derivative chapter. So let me go to here. Oh, well, it was close. I'm sorry, guys. Don't worry. We're gonna go with sections 3.4 and 3.5 to finish all the material that we're supposed to cover during this week. Okay, well, thank you.